Good morning, students. Today we start the last item of source coding in your syllabus, and it is technique is adaptive delta modulation. But before we go to adaptive delta modulation, let us go back to linear delta modulation that we have learned last time. In linear delta modulation, you have observed here, just look at this area of the curve, that when the system you have designed in such a way that if the signal is rising or falling, whatever it is, this particular picture you see is in the rising form. When the signal is rising, the accrued signal in the system is also rising, but step by step. And this step, how much it can rise, is designed. Maybe you have designed in time scale sample, you have designed each sample at 1 millisecond, and maybe the rise limit you have designed 1 millivolt. That means if the signal is rising, then at each millisecond, your measured signal will rise by 1 millivolt. But here we have talked about a particular problem which is called slope overload error. In case the signal rises faster than 1 millivolt per millisecond, of course, I said that we have to first study and observe the nature of the signal, then design your circuit. But suppose after a good design also the signal may suddenly rise faster. In that case, there is an error which is called slope overload error. And there one of you asked a question, sir, why don't we increase the step size? Instead of 1 millivolt, we make 2 millivolt. Then the problem is, if you increase the step size, then you remember the quantization error in each step is s square by 12, where s is the step height. So if you increase the step size, then your quantization error increases. Other could be you decrease the time scale. That means instead of 1 millisecond, you sample at every 500 microsecond. Then what happens? Then your measurement sample rate is higher and you have to transmit more digital bits through the channel per second per unit time. So bandwidth will be higher. So in this catch-22 situation, you may ask, sir, can there be a system where the electronics, if the electronics finds that the signal is rising faster, then it itself makes its steps higher for a few milliseconds. And when the signal, rate of rise of the signal becomes normal, then once again it reduces the step size to normal. That means, can my system adopt the nature of the signal? That is the question. Now, keeping that in mind, some clever engineers have designed this adaptive delta modulation. Adaptive delta modulation, what happens? I'll first show you the signal curve that will, then we'll go back to the principle. Here, you see, the signal is rising very fast. So, the first step size was this much, maybe 1 millivolt. And the system sensed that the signal is rising very fast. So next step size, it makes double, 2 millivolt. And signal is rising still faster. So it rises by 3 times, 3 millivolt, like that. So my system is trying to adapt to the rise or drop of the signal rate. That in mind. Now let's come to the principle, where the principle says the step size S adapts to the signal slope. That is the principle. Step size S adapts to the signal slope. If slope is high, step size increases to reduce the slope overload error. Now, there is a basic primary step size, which we call S naught or S0. Then, my actual step size can be 2S0, 3S0, 4S0, like that, right? You design a S0, then multiple of S0 can be the step size. At any sampling time, difference between the signal mt and the last estimated value m dash t. M dash t is the last estimated value. I'll go back to the picture again. Here, this is the last. Suppose I am now sampling here. My last estimated value was m dash t. So I know that in last sample, signal was much higher. So that memory I have to keep with me. Keeping that memory with me, I now decide at any sampling time, difference between the signal and the last estimated value mt measures the error. A value is created which is called ek. K is for number, sample step. K is the variable here. Here time is not the variable. Here variable is K, right? Sample number. So what it says, at any sampling time, difference between the present signal mt and the last estimated value m dash t, that difference creates the error ek. How it creates? If mt is higher, that means if the present signal is higher than the last estimated signal, then this del t is created, a particular parameter is created, delta t, which is then given to a sample level circuit. It creates ek plus 1 or minus 1. If it is higher, then ek is considered plus 1. If mt is lower, ek is considered minus 1. So this is just a sample and hold electronic circuit can serve this purpose. Okay. So I repeat once again, what we are calculating? We are calculating the last estimated value and the present signal value. If I find the present signal value is higher than the last estimated value, which indicates the signal is going up, upper side, going up and up, then my ek value is plus 1. And if I find the signal is going down and down, then ek value is minus 1. Now, the step size, sk minus 1, the present step size is sk, which is to be decided. Last step size was sk minus 1, which could be S0, could be S2S0, could be 3S0, whatever it is. Last step size is sk minus 1. And last error, ek minus 1, also is remembered. This is memorized. Of the last sampling time are kept in the memory. So what we have in the circuit, the error in the last sample, whether it was plus 1 or minus 1, the step size taken in the last sample, whether it was S0 or S2S0 or 3S0, these are kept in the memory. And the processor, this processor and accumulator makes a calculation, which is shown here. This is shown here also. It makes a calculation and determines the present step to be taken. Present step to be taken, sk, is sk minus 1. That means last step size multiplied by ek present error +1 or -1, that plus S naught is a standard value of the system, and EK -1, last error. At this moment, you may find it a little bit clumsy what it did, but I will explain how with this equation we can do the job. Say, before any sampling time, the last step size was 3S0, right? I am doing a sampling now. At this moment, I have taken the sample and I remember my last step size was 3S0 and the last error was +1. That means in the last sample also, I found the signal is going upward, and because of that, the step size was 3 times S0. And I find current sampling time also error is +1. That means now I find even now the signal is going upward. Our signal is going upward, overtaking my sample. So what will be the new step size? Now, new step size is, see the formula, Sk -1, last step size was 3S0, 3S0, multiplied by present error Ek, present error Ek is found to be 1. So 3S0 into 1 plus S0 is the standard multiplied by last error Ek -1 is given was +1. So S0 +1. So 3S0 into 1 plus S0 into 1, that is equal to 4S0. That means, now see, that means the system remembers that last sample also, the signal was overtaking my sample value, my step. And as a result of that, in last sample also, my step was 3S0, right? This is remembered by the circuit. Now I find in the present sample also signal is overtaking my sample. So I increase it from 3S0 to 4S0. By doing that, my accumulator value may overtake the signal or maybe still behind the signal. If it overtakes or if it is behind the signal, then my next step will be 5S0. If it overtakes, then my next sample step will be, we shall see what it will be, how it does the calculation. Here, this diagram shows. Now, understand this diagram. I'll try my best to explain the diagram to you. This is the row of last sample, Sk -1, last step. That means step taken in the last sample. This is Ek -1. That means the error +-1 in last sample. This is Ek, error value in the present sample. And this is Sk, that means the step to be taken in the present sample. Now see, at the very beginning, starting from here, of course, electronic circuit, starting from here, the last error was 0 because nothing is there in the memory. Last error is 0. And system designed step is S0, right? And a sample is taken. When the sample is taken, of course, it is at 0 and it finds that my signal is higher than the sample. So naturally, error is +1. So if you now put these top three values, Sk -1, Ek -1, and Ek into this equation. Sk -1 was S0, Ek was 0, so this whole thing was 0. S0 is a standard value and Ek -1 is 0. So what I am left with it is 0. So the system take one step up. Guessing system take one step up, hoping that it will match the signal. But system does not know because signal behaves in its own way, hoping. Now a sample is taken here. Now a sample is taken here. What do we find? Sk minus 1, last step. My last step was S naught, S0. And my last error was positive, plus 1, because signal was higher than the sample, signal was higher than the accumulator value. And present sample also I find signal is higher. If the signal is higher, then error is 1. Now you put these three values into this equation. Sk minus 1 was S0. Ek, present error is 1. So it is S0 into 1 plus Ek minus 1 was 1. So S0 into 1 plus S0 into 1. So it will now present step will be 2S0. So now it will rise the accumulator value by 2S0. Similarly, it will rise here by 3S0. Now, interesting is this sample. This sample. Come here, we find that S minus 1, Sk minus 1 is, I find here, Sk minus 1 was 3S0, because signal was going up and up. So I took a 3-time step. That means you take a 3-step jump, right? 3S0. And last time also my error was positive because when I took the sample, the signal was higher than the accumulator value. And when I take the sample now, I find that my accumulator value is higher than the signal value. So my error is now minus 1. If I put this value here, Sk minus 1 is 3S0 multiplied by Ek, present error, is minus 1. So it is minus 3S0. And Ek minus 1 was 1. So S0 into 1 is S0. So minus 3S0 plus S0 is minus 2S0. So now we take a 2-step backward jump. This is very interesting because I was taking one step jump, then 2-step jump, then I took a 3-step jump. Then when I find, okay, I have come ahead of the signal, so I take a 2-step jump back. I do not take 1-step jump back. I take 2-step jump back. Here I take 1-step jump up if you do the same calculation. So if you study this curve, you will find that it can definitely reduce the slope overload error. But because of this 2-step jump here, the granular noise will be slightly higher. As I said, every technique has a plus side as a negative side. The adaptive delta modulation, its positive side is it reduces slope overload error, but it increases the granular noise because it takes longer jumps. It reduces the granular noise. Now, these are the conclusions. This conclusion is very important. I'll try to explain my best. The slope overload error produces unwanted low frequency components after reconstruction of the receiver. You remember, overload error, but increases granular noise. On these two, we shall discuss next. Slope overload error and granular noise. Slope overload error increases. Now what we state here, what is the result of increase in slope overload error? Slope overload error produces unwanted low frequency components after reconstruction in the receiver. it has been found that at the receiver end, when you find then if there is a slope overload error, then at the receiver end, it produces unwanted low frequency components. And speech power is concentrated at low frequency. This in your BTech program, you do not have any subject on speech analysis. But anyway, if you can see in the net and search, you will find. By the way, let me tell you, speech analysis is a very interesting subject because all of us speak. So, what is there? What is the mathematics or what is the science behind this speech? It is very interesting. Anyway, when we speak, the lower frequency components, that means when we speak at low frequency, the lower frequency components are more powerful. But if we try to shout at higher frequency, at high pitch, that sound carries much less power. For example, if you are singing, when you sing at low frequency, low pitch, it carries more power of the song. But if you try to sing at higher pitch, then the power of that sound will be much less. Anyway, so it creates low frequency. This slope overload error creates low frequency components, and low frequency components also, on the other hand, contains more more power portion of the speech. So if you remove the unwanted low frequency components by filtering, it reduces the signal power. It reduces the speech power, right? Now, on the other hand, what we found? Granular noise. So slope overload error was reduced in adaptive delta modulation. So if the slope overload error was reduced, then unwanted frequency component was also reduced. Fine. If unwanted frequency component was reduced, then there was not much of necessity of removing them by filtering. And so the signal power is maintained. So by removing the slope overload error or by reducing the slope overload error, I have more powerful signal. But on the other hand, it increases the granular noise. Granular noise produces unwanted high frequency components. And in a filter, you can easily filter out the high frequency components because once again, if you go to science of human speech, the most of the information of the speech is in the lower part of the frequency spectrum. If you remove by some equalizer, if you remove some higher part of the frequency spectrum, you will not lose much of a speech when you hear to it. So adaptive delta modulation increased the granular noise. Granular noise increases the higher frequency components. And you can easily filter out the higher frequency components, which does not carry much of a power or information. And on the other hand, it decreased the slope overload error. If you by decreasing the slope overload error, there was not much of a disturbance in the lower part of the frequency range. So what we find, although there is a plus minus effect between the granular noise and slope overload error, over and above, if you consider both of them together, adaptive delta modulation is definitely more useful and more successful technique, I should say, because it reduces the slope overload error. This is adaptive delta modulation, right? Now, here your source coding chapter ends. Next, we shall start taking your other chapters.